So if you're aiming for a top rank in exams like JEE or KCET, there's this one chapter that, believe it or not, secretly holds the key to your success. Today, we're diving deep and unlocking the power of indefinite integration.
Now, you're probably thinking what I used to think, right? You flip through old exam papers, you see maybe one or two direct questions from this chapter, and you think, hey, can I just, skip this one? Well, let me tell you, the answer is a huge no. And I'm about to show you exactly why that is.
Here's the deal. Indefinite integration is literally the engine that powers three other huge chapters. We're talking about definite integration, area under curves, and differential equations. All of these are worth a ton of marks, and you simply cannot solve their problems if you're not a master of this topic. Seriously, think of it as the foundation of your entire integral calculus prep.
Okay, let's get down to the absolute basics. What is integration really? At its heart, it's just the reverse process of differentiation. That's it. So if you've already got your derivatives down, you've got a massive head start here.
The fancy term for it is the antiderivative, and that name tells you everything you need to know. We're given a function, let's call it little f of x, and our only job is to find the original function, big F of x, that, when you differentiate it, gives you back that little f of x. Pretty simple, right? We're just working backwards.
And this shows you exactly what I mean. The derivative of sine x is cosine x, so naturally, the integral of cosine x is sine x. But hold on, what's that plus c doing there? That, my friends, is the constant of integration. Since the derivative of any number, any constant, is 0, we always have to add that plus c to cover all the possibilities. Do not, and I mean never, forget it.
Okay, get ready for one of the most powerful and time-saving shortcuts in this entire chapter. This is what I call the golden rule, and it's going to extend all our basic formulas. You'll love this. So the rule is super simple. Any formula that works for x also works for a linear term, something like ax plus b. The only thing you have to remember, you have to divide the final answer by a, the number right next to x. So the integral of cosine of 2x plus 5 becomes sine of 2x plus 5 divided by 2. But listen, be really careful. This trick only works for linear stuff. If you try it with x squared, you're going to get the wrong answer every single time.
All right, it's time for the single most important technique in all of indefinite integration. I'm not kidding. If you can master substitution, you can solve a massive range of problems. It's the master key that unlocks all the tricky integrals.
And the whole method boils down to these 5 simple steps. First, you play detective and spot a function and its derivative, just hanging out together in the problem. Then, you substitute that function with a new variable. We usually use t. You transform the whole thing, integrate the new, much easier problem, and for the grand finale, you substitute back to get the answer in terms of your original variable.
Okay, enough talk. Let's see this in action with a classic problem. We need to integrate x squared divided by x cubed plus 1. Now, on the surface, that fraction looks like a bit of a nightmare.
Okay, step 1, identify. Let's do some detective work. I'm looking at this and I see a function, x cubed plus 1 in the denominator, and I know its derivative is 3x squared, which looks suspiciously like the x squared we have in the numerator. That's a huge clue. So let's make our move. Let's substitute t equals x cubed plus 1.
Now for step 2. We differentiate what we just did. So, du equals 3x squared dx. With a little bit of rearranging, you can see that the whole x squared dx part of our original problem can just be swapped out for dt divided by 3. And this is where the magic happens. And just like that, look what happened. That complicated mess we started with, it's transformed into the super simple integral of 1 over t times dt over 3. All of a sudden, this is a problem we can solve in our sleep. So we just integrate to get 1/3 log of t, plus c of course. And the very last step is to swap t back out for our original x cubed plus 1. And there it is, our final answer. We took a nasty-looking fraction and solved it in just a few clean logical steps. That's the power of substitution.
All right, now that we've got substitution in our toolkit, we can unlock a set of 6 special formulas. Trust me, these things show up all the time in competitive exams, and if you know them by heart, you're going to have a huge advantage.
So let's group these to make them easier to remember. The first two both have this 1 over 2a term out front. Now notice the pattern. When the x squared is positive, the top of the logarithm has x minus a. When the x squared is negative, it's a plus x.
Spotting these little details is the whole key to memorizing them.
The next two formulas you absolutely have to know are the ones that give you inverse trig functions. If you see x squared plus a squared in the denominator, you're getting an inverse tan. If you see the square root of a squared minus x squared, that's going to be an inverse sine. These two are everywhere, so please burn them into your brain.
Look, theory is great, but marks on the exam come from solving actual problems. So let's take everything we've just talked about and throw it at a real question from a past JEE paper. Let's see how it holds up.
So here it is. At first glance, this thing looks, well, it looks terrifying. You've got secant squared, tangent, and a square root, all mixed up in a fraction. I mean, where would you even begin with something like this?
The key, just like before, is to look for that function and its derivative hiding in plain sight. So, what's the derivative of tangent of something? It's secant squared of that same something. And look, we have a secant squared of root x right there. That is a giant flashing neon sign telling us to use substitution. Let's set t equal to tan of root x.
Okay, now we just differentiate, and we got to use the chain rule. The derivative of tan of root x is secant squared of root x times the derivative of root x, which is 1 over 2 root x. And would you look at that? The entire messy chunk of our problem, the secant squared of root x over root x dx, all of that just simplifies down to 2 dt. How cool is that?
And just like that absolute monster of an integral becomes the incredibly simple integral of 2t dt. The integral of that is just t squared, we swap our t back in, and we get our final answer, tan squared of root x plus c. See? That's how you take a scary-looking JOE problem and turn it into just a couple lines of work.
So, the big question is, how do you get so good that you can spot these patterns instantly? Well, it's not a magic trick. It's just practice, and a lot of it. The expert from our source material said it perfectly. When students solve hundreds of questions, the confidence they get is on a completely different level.
That's the number to have in your head. 400, maybe even 500 questions. While for other chapters you might get away with 50 or 100 problems, integration is a different beast. It's this high volume of practice that actually trains your brain to see the patterns and solutions almost without thinking.
At the end of the day, indefinite integration isn't just another chapter. It's the bedrock for your entire calculus skill set. Mastering it is what sets you up for success in so many other high-stakes topics. We've covered the theory. Now the only question is, are you ready to get to work and build that foundation?